In the first revision question in geometry, we have some calculus involved too, but this is the order that the study cliques give them. So let's have a look here. Another ornament is made of two cones inscribed in a sphere. The top cone is upright. So in this left-hand diagram, we can see the cone here with circular base. A vertical cross section of the ornament taken through the center of the sphere shows the cones as two triangles ABC, which is the top triangle here. So we're just focusing on the triangles in this one, and ABD, which is the bottom triangle, this one here. And we're asked to show why the angle CBD is 90, this one here. So this is kind of like a junior cert question. We have a diameter of a circle. The angle standing on the diameter is 180, and any angle standing on the same arc is half the angle at the diameter. So this one here is definitely going to be 90, and you can write in angle standing on diameter of a circle equals 90 degrees or something similar. In the second part, we're asked to prove that the triangles BCE, so let's write them beside the diagram here, BCE, this one here. What do we already know about this triangle? Well, it has a right angle. We'll number these 1 and 2, and below BCE, the other triangle is DBE, so as a common side. I know it's not the scale, this one's a lot smaller, but just so we can see that it has a right angle in here. They both have right angles. We'll number this one 3 and this one 4. And what do we know so far? Well, we know, coming over to the left, that the angle 2 plus the angle 3 is equal to 90 from part 1. From the top triangle, because of the right angle, angle 1 plus angle 2 is equal to 90. Therefore, if we look at these two expressions, they both have angle 2 in them, so therefore angle 1 has to be equal to angle 3. They have a common side. We call it EB as the common side. So jot down everything that we know. EB is equal to EB, and similarly in the bottom triangle, angle 3 plus angle 4 must be equal to 90. Three angles in the triangle add up to 180. So therefore, based on these two equations, the top two, we can say that angle 4 is equal to angle 2. So without the common side, three angles equal. And therefore, they are similar. In part 3, we're told the top cone has a radius of r and a height of h. So let's draw the two triangles out again. Or we can just use the triangles we already have here. So they're told us that EB, which we can see here, EB, the common side is equal to r. So both of these are r. The blue ones are r. And we're told EC is equal to h, so that's this side here. This is h. And we're also told that the radius is 10. So if the radius is 10, this diameter is 20 all the way down. So this one would have to be 20 minus h. And we're asked to use similar triangles to show that r squared is equal to 20h minus h squared. So we take the two angles that were the same. If we draw them out like this, maybe with symbols, sometimes it's easier to see. So we have a right angle. I'll do a dot and a circle in the top triangle. In the bottom triangle, we have a right angle, and we were told that we know that 1 is equal to 2. Sorry, we know that 1 is equal to 3. So if we do the dot up here, that's 1. 3 is this dot. So this is the circle. So using similar triangles, if we start with r in the first triangle, we can say that r over the similar side in the other triangle is the right angle to number 2, or the right angle to the circle, which is this one, 20 minus h. So r over 20 minus h equals, we have this h, and in the other triangle, from the right angle to 1 is the right angle to the solid dot, which is this side here, or, and if we cross multiply, we're going to get r squared is equal to 20h minus h squared, which is what they were looking for in the second part. The next part is calculus, not really geometry, but we'll do it anyway. We're asked to write the volume of the top cone in terms of h and pi. The volume of a cone is equal to 1/3 pi r squared h. They don't want any r in it, they just want h and pi, so we got to replace r squared, which we have here. So the volume of the cone is 1/3 pi by 20h minus h squared times the other h that's already in there. So we tidy this up. The volume of the cone is 1/3 pi by 20h squared minus h cubed. And if we want the max, we differentiate and let it equal 0. So we have volume and we have h. So dv dh, in this case, pi over 3, I'll write it as pi over 3, that's the constant at the beginning. So if we differentiate the bracket, we're going to get 40h minus 3h squared. So if this is equal to 0, pi over 3 can't be 0, this guy has to be 0. 40h minus 3h squared will be equal to 0. And if we factor out our h, there's going to be two values here, 40 minus 3h. So h will be equal to 0, which it can't be. We can't have a 0 height. So 40 minus 3h is equal to 0. 3h is equal to 40. So h is 40 over 3. So geometry, not really a standalone question anymore. Mix it into other types of questions too. Question 2, we have O is the center of a different circle. It was part C of another question, this geometry question. A and B are points on the circle, so we can see A and B. The chord AB is extended through B to C, so that BC is equal to the radius. So here's the radius, BC. We know that this is a radius. We know that this is a radius, so fill in what we know. CO intersects the circle at D, which we can see here. Here's D. With D and E, an element of CO. Let BCO equal X. BCO is this one here. This is X. Write AOE in terms of X. Okay, AOE is this one here in terms of X. So where can we start with this one? Well, because this is a radius and this is a radius, we have an isosceles triangle, so this angle in here must be X. And then we have three angles in a triangle, so we can get this one here is going to be 180 minus 2x. So we might just label what we've done there. We'll say BOC, the angle BOC is equal to x, because BO, the length BO is equal to R. Therefore, isosceles triangle. And I think that's enough information to show that. And we can say the angle, just do it here, the angle CBO is equal to 180 minus 2x. Why? Because three angles in a triangle add to 180. So geometry is really about simple steps. Just show and tell the examiner what you're doing each time. So can we get this one here next? I think we can. That's the angle ABO, the angle ABO, straight line, with the other angle beside it is equal to 180 minus the angle beside it, which is 180 minus 2x. The 180s will cancel here, so the angle ABO is equal to just 2x, just because of a straight line. seems like we're working our way towards where we want to be. So this one in here, 2x. This is also a radius, AO. So AO is equal to OR. Therefore, the triangle ABO is equal to isosceles. It has two radiuses. Therefore, the angle BAO, they're both at the end of the radius, this one here, is going to be equal to 2x as well. I think we're nearly there. Therefore, this one in here is going to be 180 minus the other two. Therefore, the angle, and that's BOA, is equal to 180 minus 2x minus 2x, which is 180 minus 4x. I think we're nearly there. So we have this is 180 minus 4x. So this one in here, the angle AOE, is equal to 180 minus the two angles beside it, which is 180 minus 4x, and this one here, which is just x, so minus x. So the angle AOE is equal to 180 minus 180 plus 4x minus x, which is equal to 3x. So a lot of knowledge, isosceles triangles, straight lines, that kind of stuff comes into this question. Quite a lot of work involved, but the maths, as you can see, is pretty straightforward. In the next question, we have to state whether the following statement is true or false. Two angles are vertically opposite if, the important bit in this question is if and only if they are equal in size. Two angles are vertically opposite. If they're equal in size, they don't have to be vertically opposite. If this is an isosceles triangle, if we have x and x, this angle 1 is equal to this angle 1. So in isosceles triangle, two angles are equal, and they're not. I'll just write VO for vertically opposite. I think that's what they're looking for here, or something similar. And then two diagrams below show the same rectangle, not drawn to scale. We're asked to prove FE is equal to EH. So we've extended here to EH, this bit. And if we look below here, we have this angle is theta from here. And with our Z, we have this angle is theta. And from the diagram, to the left, this angle is theta in here. We also have a common side in here, ED, and we have two right angles as well, here and here. So if we lay that information out, the angle FED is equal to the angle DEH, both 90. We're asked to show that FE is equal to EH. Okay, so we have the common side. The length of ED is equal to the length of ED. That's a common side. And what else do we have? We have the angle DFE is equal to the angle DHE, both theta from the diagram. And we might say that just that's because the angle DHE is equal to theta because it's alternate to the angle that we showed, which was this one down here, DBC, the angle DBC. The third angles have to be the same as well. So the angle FDE angle EDH. Therefore, triangles FED and EDH are congruent. Therefore, FE is equal to EH. That's that question. And then the next one, we're asked to find the angle theta. Hence, or otherwise find the angle theta. So if we come back to the diagrams, we've just proven that these two are the same in here. And we're told the length of AB at the beginning, the length of AB from this diagram is 20. So these are 10 and 10. So that's 10 and it's 50 all the way across the bottom here. This one has to be 40. And we have theta in this triangle. And we have a 90 along here. So what have we got here? We don't have the hypotenuse, so it looks like tan. So the tan of theta is equal to opposite over adjacent. The opposite one in this case is 90 and the adjacent is 40. So just coming below here, if we type into our calculator the inverse tan of 9 over 4 or 90 over 40, we're going to get 66.037 degrees, and we're asked the nearest degree, so 66 degrees is what theta is equal to in this first revision video for geometry.